lost the first part of that. I paused it. All right, so the next force that your book goes into is called the normal force. If you know the mathematical definition of normal force, or what normal is, who knows what mathematical definition of normal is? Right, tell me. What is it, Kiyosha? It's perpendicular. Very good. So normal means perpendicular in a mathematical sense. So normal means perpendicular. So the normal force is an equal and opposite force in opposition to another force. As Kiyosha, right? As Kiyosha said, it's perpendicular. It is always perpendicular to the surface. So, for example, if I stand here and I push on the board with a certain force, I wish I had a force vector for an arm. Wouldn't that be cool, like in the picture? If I push on the board here with a force of, 10 newtons or whatever, the board is going to push back on me in the equal and opposite direction with also a force of 10 newtons. And that will be the normal force. So if I put 10 newtons here, my normal force, which is exerted by the board on me, is going to also equal 10 newtons. So I'm going to call this F with an N subscript, and it's going to be 10 newtons. Likewise, if I stand here on the ground and I have a force weight that is acting downward, typical person weighs about 700 newtons. If my weight is 700 newtons, the earth is pushing back up on me with that same force. As you saw with the scale too, you push down with a certain amount, then you get that same force pushing up, 700 newtons. Or if I have a higher weight, or if somebody is pushing down on top of my head, say somebody is pushing down here on top of my head with 100 newtons of force, what is going to be the normal force now? What is it? No, it's going to be 800. So imagine here, I have this table. This is going to come up with friction, okay? So it'll be important. If I have this table and say this table weighs, I don't know, 30 newtons. All right, it weighs 30 newtons roughly. Not quite that much, 20 newtons maybe. If I push down on it with 5 newtons, or rather, excuse me, if I don't push on it, then the floor is pushing back up with 20 newtons. But if I push down on the table, I'm adding an additional force. So now it's going to be 20 plus whatever I'm pushing on it with. All right, so here I've increased the normal force. The normal force is now 700 plus 100 newtons, which is 800 newtons. Okay? You're not really going to use that except for friction because your normal force actually affects the friction. Okay, now let's look at friction. This clear on the normal force? Yeah? It's always perpendicular. And in your book, they have a pretty good discussion of normal force as well. And now, finally, friction, or two more. Friction. Friction is the force between two surfaces in contact. All right. Don't write this down, but I think this is very interesting, so I'm going to tell you. But it's not in your book, and it doesn't really come up again, so you're not responsible for it. But there are two types of friction. There are macroscopic and microscopic, but please don't write this down. All right, so if you're writing this down, please don't do it. Two types of friction, macro and microscopic. And of course, macro, that means big, right? So when I talk about macroscopic friction, it's like I have these two surfaces that are really ragged, and they come together. And because of those, the forces in between, like the crags and the crannies of those two surfaces, you experience friction. You would expect that, right? Like if I have two pieces of sandpaper, they're going to sort of fit together like that, and they're going to be difficult to move across one another. They're going to have a lot of friction. But a funny thing happens if you take those two surfaces and you make them really smooth. So now if I have one surface and another surface, you would expect the friction to decrease, right? Right. And actually it does. Like if you plot the frictional force versus, let's call it the amount of smoothness, this meaning this is really rough here, and this is really smooth here on this end, then you're going to have a very high friction here, and then it's going to decrease the amount of smoothness, but at some point it's going to increase again. Can you imagine why, as you smooth those surfaces, the friction will eventually begin to increase again? This is really cool. You're going to be wow. Like you're going to be telling your friends about this all afternoon. When you make those two surfaces really smooth, you basically get the atoms within the materials closer together. And so you get away from macroscopic friction, where you actually have nooks and crannies, to microscopic friction, where now you're actually having interactions between the molecules within the material. So you have positive and negative charges that are attracted to one another in the microscopic friction. And then that actually causes them to be stickier. Don't write that down. I think it's really neat. Okay, so the friction is the force between two surfaces in contact. There are two types of friction. You do need to write this down. There is static friction, and then there's kinetic friction. The static friction is acts on stationary bodies. I'm going to call it F, a lower or a script F like that, with an S subscript for static friction. And kinetic friction I'm going to call script F with a K on it, kinetic friction. And you might imagine that this acts on what type of bodies? What? Moving bodies, right? Moving. All right. Another thing about friction is that friction is proportional to the normal force. I'll show you how that is. So friction is proportional to the normal force. When I say that it's proportional, that means that if the normal force increases, what happens to the friction? It increases as well. So if Fn goes up, then the frictional force will also go up. They're proportional. If you do one to one thing, the other happens to the other. So imagine this table. If I try pushing it across the floor, then I have a certain amount of friction that impedes me pushing it across the floor, right? And according to Newton's first law, actually, if I push it and let it go, it's going to keep going on forever, right, until a force acts upon it. And the force that acts upon it is friction, right? So, however, if I increase the normal force, remember how we did before, if I push down on the table and increase the normal force, is it going to be easier or more difficult to push? It's going to be more difficult because by increasing the normal force, I increase the friction. And you probably know that intuitively, right? What's a good way to move this across the floor with making it a lot easier? Like easier than this. I can do what? If I had wheels on it, yes. What? Right, you pick it up. Right, so, but say I don't want to pick the whole thing up because then there's no friction at all, but I can pick it up a little bit, right? And so if I pull it like this, it's a lot easier. Because by pulling up on the table, I've done what to the normal force? I've decreased it, right. So by pulling up, you decrease the normal force. So if I decrease the normal force, my friction decreases. If I increase it, my friction increases. All right? Now, something else about friction, and I have a little clip I want to show you that illustrates this, is that static friction is almost always, I think it is always actually, is always bigger than kinetic friction. And you know this too, actually, just from experience. If you have a big box in your house and you want to push it across the floor, or a big piece of heavy furniture, it's always more difficult when? To get it started or to keep it moving? To get it started, right? You have to have like an initial big push to get it moving, but then after you get it moving, then it's a lot easier because the kinetic friction is less. You can also try this in your car. You might not have experienced this before, but today when you leave, uh, you're driving in your car, whatever kind of car you have, and you come to a stop sign. Now, usually I know that you just blow right on through the stop sign, right? But today I want you to come to a complete stop and do it very slowly, okay? So step on your brake and then come to a very slow stop. And what's going to happen just before you come to a complete stop? Right, it's just going to it'll sort of lurch forward a little bit. And that's because inside your wheel you have a rotor, and then there are brake pads that clamp down on that rotor, and they give you friction, right? Now, as the rotor is turning, that's what type of friction? That's kinetic friction. But just before it stops, it makes this transition from kinetic to static friction. And since those two forces are different, right, that kinetic is actually smaller than static friction, that causes this discontinuity and causes you to sort of lurch forward. Okay? So you can do it as you're headed out Maidwood. Then you go to that stop sign. Just come to a very slow stop instead of just barreling all out into Highway 1. Okay? All right. When I first took my now wife, out to Mississippi, where I grew up very rural Mississippi. It was like 20 miles from a town with like 1,000 people. And all the stop signs out there, they're sort of suggestions. But not all of them, because some of them, if you run them, you'll get splattered by a pulpwood truck. Yeah. But others, you know that you can sort of go through them without any issues. But she had a lot of difficulty because she's sort of all about stopping at stop signs, like the whole law thing. She likes following it. Okay. And then finally, there's one more force. It's fairly simple, but it comes up, and it's going to come up later when we talk about muscles, and that is tension. Because the force that we experience in our muscles is a tension force. A tension is a force in a rope or string or some other type of material, or muscle as it may be, between two objects. All right. I think that's really all we need to say about it. Yeah, I think that's really all. It'll come up again when we talk about it. One point, though, I do want to make is that let's say that I have a tug of war. All right? And I have a rope between these two guys. All right? I'm pulling with a force over here of 100 newtons. And then this guy is pulling over here with a force of 100 newtons. And nothing's happening, right? Because we're both pulling with the same force. And so my net force here, if I add up my net force, what is it going to be? Is 0. It's 100 minus 100. It's like the car, except here they add up to equal 0. But what is the tension in the rope? What's the tension in the rope? Let's try to get your clickers out. We're about to use them anyway, but go ahead and get them out. I want to ask you a question. Is the tension, is it equal to 0 newtons is it equal to 100 newtons, or is it equal to 200 newtons? 0, 100, or 200? We're going to try that out. Hmm. All right, I'll stop at 50. 5 more seconds. Just guess if you don't know. Let's see. Most of you put 200. All right. So let me show you here. I meant to bring some string, but I forgot to bring it. So we're just going to use this old nasty towel right here. How's that sound? Is that okay? What's your name? Ashley. Hold that, please. All right, now look. Ashley and I have a rope in between us, and now I'm going to pull on it. Why don't you pull, Ashley? Don't. All right, so it looks like I'm pulling with 3 newtons. How much are you pulling with, Ashley? 3 newtons, right. So we're both pulling with 3 newtons. All right, so what do you think is the tension in the rope? 3. All right, let's say that we're going to take this, and I'm just going to hold it right here. All right, now I'm just like a tree or something, like it's tied to a tree, and now pull with 3 newtons. And now what do you think is the tension in the rope? 3. Let's try this question again. See here, most of you put 200 newtons. Let's try it again. About 10 more seconds. Or I'll give you till 30 just to get your answer in. At 38, I'll stop. Okay, B is the right answer. We'll see this come up again on the concept test in just a second. So this might trouble you because you're both pulling with 100 newtons, right? It seems like there should be 200 newtons of force in the rope. But imagine instead of having a person here, imagine that instead that you have a what? A tree, right. And then you're pulling on one end with 100 newtons. And the tree is also pulling with 100 newtons, however. So you only have 100 newtons in the rope. All right, let's try some questions here. Get your clickers out. I will post these on the website. All right, I'll stop at 50. Just guess if you don't know. Remember, guys, on these questions, even if you get the answer wrong, you still get credit. If you get them correct, you get twice the credit. Let's see what y'all got here. Oh, boy, we're all over the place. Okay. Think Newton's first law. All right. I have a book resting on a table. The book will remain there at rest because which of these? There's a net force, but the book has too much inertia. Now, Newton's second law says that if there's a net force, a non-zero net force, then it's going to do what? Remember, the second law is the law of acceleration. So if there is a non-zero net force, it has to accelerate. It can't be A. There are no forces acting on it at all. Is that a true statement? No, there are lots of forces acting on it. In fact, we've just said two of them, right? What are two forces acting on it in those list of forces that we had? The weight and the normal force, right? The weight and the normal force, right? So there are no forces acting on it at all. It does move, but too slowly to be seen. No, that doesn't even make any sense. All right. And then E is really just a restating of A. Let's try it again. Stop at 20. Okay, D is the right answer. Good job, 12 of you. They got it right the first time. That was good. All right, there's no net force on the book. All right, a hockey puck slides on ice at a constant velocity. What is the net force acting on the puck? Now, we didn't really talk about velocity. If something's moving at constant velocity, what is its acceleration? It's zero, right? So if it's moving at a constant speed or velocity, that means it's not accelerating. It has zero acceleration. I'll stop at 50. 5 more seconds. Oh boy, okay. Okay, let's go back to our law of acceleration. If our law of acceleration says that the force or the acceleration is proportional to the force and the mass, right? So if I have a big force, I have a big acceleration, all right? And so here I'm telling you that the acceleration is what? Is zero. So now we want to know what is that net force acting upon it. Try it again. Remember, you're welcome to talk to your neighbors or look in your notes or whatever. This is just for practice. I'll stop at 25. Okay, E is the right answer. If I have no acceleration, I have no net force. Good job, you guys. All right, you put your book next to you on the bus seat. When the bus stops suddenly, the book slides forward off the seat. Why did it move forward off of the seat? This is going to really test your Newtonian versus Aristotelian views of motion, because most of you are Aristotelian, not Newtonian. Stop at 45. 45. What is the net force that acted on the book? Think about that. What is the net force? There is no net force acting on it. What's that? Remember, if there is a net force, it's going to accelerate. But does the book accelerate? No, the book is just keeping on moving like it's been moving, right? Think Newton's first law. If an object is in motion, it'll tend to stay in that state of motion. What is the state of motion of the book before the bus stops? It's what? It's not at rest, no. It's moving with the bus. Huh? When the bus stops, but the book keeps on moving. Let's try it again. A is not the right answer, by the way. Y'all try it again. All right, I'll stop at 25. Okay, B is the right answer. Did I coach you into that, or do you understand? Huh? Okay. This goes back to the difference between Newtonian versus Aristotelian physics. This was the incorrect law of motion. A was the incorrect law of motion. That when something, that the book is moving along at a constant speed in the bus, at the speed of the bus, but when the bus stops, the book keeps moving at that constant speed because a net force didn't act upon it. There was no net force acting upon it. What if the book didn't slide off the seat? What would the force have been acting upon it? What force would have acted upon it? But either the force of your hand holding it on the seat or the force of friction holding it onto the seat. Right? So if the book stays on the seat, it's because some force acted upon it. If the book doesn't stay on the seat, it's because there was no force acting upon it. It just slides right off. Okay. That's a tough question. All right, you kick a smooth, flat stone out on a frozen pond. The stone slides, slows down, and eventually stops. Which of these do you conclude? I'll stop at 45. 5 more seconds. Just guess if you don't know. Hey, very good. Y'all are getting better. So y'all are getting more Newtonian, because C is the right answer. Well, 54% of you are getting more Newtonian. All right. Uh, the Aristotelian view, that is before Newton, pre-Newton, these two would have been the right answer. Like before they had this idea about motion, that either it just sort of ran out of steam, it had this sort of ethereal force behind it, this ethereal energy within it, or that it has this natural state to be at rest. Remember, Aristotle thought that everything, its natural state was at rest. But the fact is that there's a force acting upon it, and that force is going to be the frictional force between the ice and the rock or the stone that acts on it all along to slow it down. So it has a net acceleration not equal to 0. Let's try this one. What will happen to this cart? You push it on a frictionless table. What will happen to it? I will put these online for y'all, by the way. Stop at 40 seconds. Okay, we're all over the board here. Okay, Newton's first law. An object that's in motion will stay in motion. An object at rest will stay at rest. Whatever its state of motion, because of its inertia, it's going to have this tendency to stay in that state of motion. Here I have a cart on a frictionless table, so we can say that there are no forces acting on it, no net force. But I push it and let it go, and I want to know what's going to happen to it after I let it go. Will it accelerate, continue with either constant or decrease in acceleration, come to a stop, constant velocity, that means move at a constant speed, or immediately come to a stop? Think Newton's first law, that if it's in a state of motion, it's going to continue to be in that state of motion unless a force acts upon it. Let's try it again. Stop at 20 seconds, so 10 more seconds. And we'll stop these in just a few minutes as well. Oh, it is D. Okay, I'm sorry. I thought that was E. Yeah, D is the right answer. It's going to continue with constant velocity. After you put it into motion, it's then in a state of constant velocity, and it will continue in that state forever, right, until a force acts upon it, or it runs off the table. Right, so D is the right answer. Okay, y'all are getting better at these. It just takes practice. This is sort of a different way of thinking about things. All right, what would you have to do for the same cart to move it at a constant acceleration, continually speeding up? What would you have to do to the cart? I'm going to stop at 40, or I'll stop at 42. Hey, good job. You have to push it continuously. That goes back to our Newton's second law, the law of acceleration. In order to accelerate something, it has to have a net force. I have a truck, and this fly zooms along and says, wham, right into its windshield. What happens to the truck? It's sitting on ice, so there's no friction at all. What happens to the truck? I want to know what happens to the truck in the instant that the fly smashes into its window. In that instant, when the fly runs into the truck, what happens? We'll make this the last one. It's a few more seconds. I'll stop at 55. Now, the answer is C. I'm just going to tell y'all. It's applying a force to the truck. It's a really small force, right? But if you truly have no friction acting upon the truck, then it's going to accelerate backwards in that instant that the fly hits the truck. Now, the other answer that is not entirely correct because of that caveat that I said, in that instant that the fly hits it, what's going to happen after the fly hits it? It's not going to be C, it's going to be what? It's going to be B. So after the fly exerts its force onto the truck, that truck is going to move back at a constant speed. A really small speed, no doubt, right? But a speed nonetheless. All right, we'll have some more of these. Next time we're going to move into muscles and joints and stuff. Though, as I said, your quiz today will cover some of that information because it was in Chapter 1. But you didn't know that? I sent an email out about it. Oh, that's true, right? Okay. Listen, we'll have 5 quizzes. We'll have 6 quizzes. We might have more than that, and I'm going to drop the lowest one. Or if we have 7 quizzes, for example, I'll drop the lowest 2. Or if we have 10 quizzes, I'll drop the lowest 5. But I suspect we'll just have 6. These are just meant to be a quiet and easy place for you to practice for the exam, which do count a lot more. These don't count a whole lot. Listen, folks, it's multiple choice. There are 10 questions. I want you to write the answer right next to the number. All right? I'm not requiring you to use a Scantron. I'm going to try it without it. But to help me, please just write your answer right next to the number, very clearly, okay? Where are you going to write your answer? Next to the number, right. It doesn't matter, pen or pencil.